All right. Let's go ahead and get started. I did not kill a bunch of trees today. In fact, the handouts that I gave you all last time are basically the ones we're going to use today. So no significant issue there. Also, if it makes you a little more relaxed or calm and what have you, I do not have a homework for you this week. So you all had a pretty significant homework last week, which was due today, so I figure we can calm down a little bit. One of the reasons, though, for this pause in homework is we need to begin the discussion of an exam, which is, first off, if you've had me before, you know I don't like to call them exams. I like to call them celebrations of learning. So we have to plan a celebration. However, since this is a night class and it is a once-a-week course, what I'm going to do is a take-home exam. Okay? It's going to be a pretty straightforward assessment of all the section properties and loads stuff that we've talked about since the beginning. So I guess a fair point is starting now, this is all exam 2 material. Everything from here before to day 1, that was all exam 1 material. And I'm going to, I think, follow a model that I did in finite elements in previous semesters that I think worked out pretty well. What I did for finite elements is instead of, we have 2 exams in this course, and instead of saying, exam 1, week 8, exam 2, week 16 or whatever, I think I might do exam 1 next week and then exam 2 probably like week 13, week 14. And then that way, from then to the end of the semester, all you have to worry about is the design project. So hopefully that lessens your stress level as you prepare for finals and your comprehensive projects and your senior projects and all that. All right, so sound good? So hopefully that'll offer a little bit of a respite near the end. Okay, I actually just left a presentation on the rehabilitation efforts on the Mosel Dam. The presenter who was presenting was using my clicker, so if at any random point some student walks in and hands me a remote, it's the clicker, so the presenter's still using it, so don't freak out. Okay, so let's go ahead and get into the lecture. So I would argue that everything from week 1 to week 5 that we covered is what I like to call maybe part 1 of this class. Oh, there's this student I mentioned. Wait. The thing. Oh, there it is. Oh, thank you. The receiver. There we go. All right. Everything that we covered from week 1 up until the beginning, everything from week 1 up until now, is what I like to call part 1 of this course, where we talk about the loads on bridges. And while we spent all of our time talking about steel girder bridges, a lot of this stuff would translate to pre-stressed concrete girder bridges as well. I mean, it's still the same loading sequence. It's still the same elastic section property theory, elastic bending theory. A lot of the live load distribution factors are the same. We just reserved our discussion to a particular type of bridge to make the discussion a little easier. Everything we're going to do now is going to look on the other side of the equation, looking at resistance. Okay? So instead of looking at how much load, how much moment, how much shear, and all that is being placed on a beam, now we're asking how much can this beam resist? What is its moment capacity? What is its shear capacity? So that's going to take a little bit of time. Before we can just say, well, here's the moment capacity, here's the shear capacity, we need to sort of take a step back and review some fundamental properties. Kind of like what we did with loads. Before we started diving into loads, we said, let's go back and talk about moments of inertia and section moduli and things like that. We're going to kind of do the same thing. So I'm going to take a step back and review some fundamental properties of beam resistance. Okay, so this might seem like a hodgepodge of different stuff that I'm talking about, but there is a point to it, because later on, when I mention R sub H or D sub CP or what have you, I want you to at least have an idea of what all that stuff means. Sound good? Okay. So one of the things I want to handle right off the bat is the differentiation between a beam and a plate girder. Now, that might not make a whole lot of sense right now because up until now we've probably utilized these terms interchangeably. If I'm looking at a two-span bridge and I'm looking at those flexural elements, I probably refer to them as beams and plate girders, interchangeably. But there really is a fundamental difference in the behavior, so much so that the spec is actually written based on this differentiation. Okay? When I think of a beam, I think of the top flange, the web, and the bottom flange all working together as one cohesive flexural element. When I think of a plate girder, I don't think that. I think that the members, the elements, are so slender that the compression flange and the tension flange are sort of acting on their own. If you've taken a course in steel design, you probably remember that whole concept of lateral torsional buckling, the idea that you place a load on a beam, the part of the beam is seeing compression, the other part's experiencing tension. From mechanics, you all know that things in compression like to do this thing called buckling. Remember that? Well, the part of the beam wants to buckle, part of the beam doesn't. There's this internal conflict of stress, and this is resolved by the beam kicking out and twisting, right? Well, beams, if we're looking at a beam, the whole beam would want to kick out and twist. Plate girder, not so much. Really, the compression flange and a certain portion of the web is going to want to kick out and twist, not the whole thing. Because the web and those elements are so slender that it's not really wanting to act as one cohesive unit. So there's a fundamental difference in behavior between how a beam behaves and how a plate girder behaves. So much so that later on when we look at the spec, we will see how the spec is written according to this philosophy. When we go to the main body of the spec, 610, it'll be written for plate girders, but there's going to be a further section in the back, Appendix A, that's written for beams. But we'll get into that. So in order to have a general discussion about beam capacity, in other words, how much load can a beam resist, we have to look at the different types of failure mechanisms that a beam can exhibit. In other words, if we know how a beam will fail, we can determine, well, how much load would cause this particular failure mechanism. Then we can say, all right, if we know how much load causes this particular failure mechanism, that is its level of resistance. We can't exceed that or it's going to fail. Then we have a measure of resistance that we can compare against loads and see if the element is safe. So let's talk about beam failure mode. So primarily we can experience yielding, which beam yielding is its own sort of special consideration. You've probably at least heard of the idea of a yield moment versus a plastic moment. If it's been a while since you've talked about that, no big deal. We're going to cover it in significant detail. We're going to spend a lot of time talking about the different ways that beams can buckle. They can buckle not only in a global mode, the whole beam wanting to kick out and twist, but also in a local mode. Maybe the whole beam doesn't buckle, it's just a flange that buckles, or just a web that buckles. Maybe it doesn't buckle in bending at all. Maybe it's the shear that causes the element to fail. Maybe it yields in shear, it buckles in shear, excuse me, and what have you. We'll spend some time talking about that. Plate girders, because they're a little flimsier and because they are a little more complicated in terms of the mechanics, there's a little bit more stuff going on. We can have compression flange buckling, compression flange, lateral torsional buckling. We can have vertical flange buckling of the girders. And don't worry, we're going to spend a fair amount of time talking about a lot of this. We'll also go into this concept of tension field action. This is a phenomenon in the web where the web can actually resist load beyond buckling, which is somewhat of a strange notion, but it happens very readily in a plate girder element. All right, so let's begin our discussion by reviewing non-composite beam behavior. In other words, just the steel shape by itself. And a lot of this stuff, if you've had a course in undergraduate steel design, you'll have seen before. Might have been a while, but that's okay. You probably should have seen a lot of this stuff in some fashion. Okay? Now, let's just go back to basic mechanics. Okay? So beams are one of, if not the most fundamental element in engineering, period. So if you don't know how a beam works, you're in the wrong class, right? In some fashion or another. All right? What we're going to do is, right now, is look at the basic fundamentals of how we get stresses in beams. And a lot of this, I think, you'll think is a somewhat old hat. All right? So let's just go back to basics. We've got some beam. It's subjected to whatever loads, distributed loads, point loads, whatever. Now, I can cut a section. If I cut a section in this element, I can have at most 3 unknown forces: an unknown axial force, an unknown shear, and an unknown moment. That should be old hat by this point, right? Okay. Now, going back to mechanics, as we'll see in a moment, no pun intended, if I cut a section, that axial force P generates normal stresses. You know, sigma equals P over A, right? We also get stresses from bending moments and from shear forces, and we'll deal with all of these in their own time, but I want to look at these bending moments first. Okay? Now, to derive the stress equation for beam bending, we got to make a few basic assumptions. So we start off assuming linear elastic behavior, you know, Hooke's law. Everybody should be okay with that. We assume strength compatibility, plane sections remain plane. In other words, all we're saying is that from the centroid, the deformation is proportional. And we assume small deflections, which we'll actually probably spend a little bit of time talking about this idea of small deflection versus large deflection theory, because that can get pretty funky if you've got some second-order effects that you need to consider, which definitely happen. One of the at least readily direct applications that we'll need to consider is lateral flange bending. It's a particular type of twisting that occurs in beams like bridge elements when they're twisted. And a simple example of a bridge beam being twisted is during concrete deck placement, because you have your overhang forms on the exterior girders and they want to twist those exterior girders. So we'll need to consider the large deflection aspect, and we'll talk about what that means later. All right. Now, if we use these basic assumptions, we look at some random beam. It's got some random arbitrary cross-section. You know, normally for us, we would think of this as an I-beam, but it can be any shape. It really doesn't matter. Okay. Using statics, we can determine the P and M inside the beam. We know those are going to generate normal stresses. So what's that going to look like? Well, if I have two equations, or if I have two unknowns, and I want to, or let me put it like this. If I have an unknown stress profile, and I've got at most sort of two unknown components that go into that, probably a reasonable assumption is that that stress profile is somewhat linear. And this is, not to go too far off on a tangent, but this is actually really similar to I guess a finite element approach when you're looking at shape functions. When you have two known values, you assume a linear function. When you have three unknown values, you assume a quadratic function, and so on and so forth. I know my finite element folks should remember all this. I know you all had a lot of fun deriving that three-noted bar element, right? You can see you starting to, you know, shake a little bit just thinking about it, right? Yeah, they're getting a kick out of it. All right. What we're going to do is we're going to make an assumption that this stress profile is linear. And then based on the forces that we know, we're going to see if we can determine what these constants are. So let's take it one step at a time. So we're assuming that the stress profile is somewhat linear. Okay? So we've got two unknown constants, but we've got two known force components on this system. We've got an axial force P and a bending moment. So two unknowns, two values we do know. We should be able to solve for these pretty readily. All right? So after going through and doing all the math, we get something that looks like this. And if you want, I'm more than happy to go through this derivation with you, but I have got to believe that by now you recognize some of these aspects. In other words, the constant stress at C sub 1 is really just P over A, the stress due to the axial load. And the bending stress due to the moment is sigma equals my over I. Do I need to derive that, or are we accepting that as gospel by now? Sound good? Okay. Now, so if we're only considering bending stress, we've got sigma equals my over I. Fundamental basic bending stress formula. Okay, now, so right off the bat, we should see some quantities that we should be very familiar with in this course. I mean, sigma equals my over I being that moment of inertia. If you can't compute the moment of inertia of an I-beam by now, especially after homework 1, where we developed this massive Excel spreadsheet to do that for us, you know, you'd probably be in some trouble. But by now, we should be pretty good on that. So far, so good? All right. Also, the idea of a section modulus. You know, if I have a moment of inertia and I have a stress profile, I recognize the largest stresses are either going to be at the way tippy top of the section or the way, you know, very, very bottom, right? So I can say, all right, let's take that moment of inertia, divide it by, remember, an extreme fiber distance from the centroid to that extreme-most fiber up top or that extreme-most fiber on the bottom, and generate a section modulus. Remember that? Now, if you've got a symmetric section, you're going to have the same section modulus on top as you are on the bottom. But by now, you should recognize that in bridge elements, that's not the case. I mean, we've been having, what, like 14 by 3/4 inch top flange and 16 by 1 1/4 inch bottom flange. It's very common for the flange sizes to be different because you're tailoring those flange sizes for their specific load demand. And by the end of the semester, it will become very clear that compression flanges and tension flanges experience different phenomenons and stresses in different fashions. So if it's not already clear now, it will be later. All right, so what we can do is if we say, all right, we know a section modulus, we know a limiting stress for a metal, a very common limiting stress would be the yield stress, Fy. I can compute a yield moment as saying Fy times the section modulus. Now, one thing I'll point out, this is a very simple calculation if you're dealing with a non-composite beam. If you're dealing with a composite beam, you can't just take Fy times the section modulus and get a yield moment. It's a little more involved, and you'll see why later. But so far, so good? Okay. Now, all right. And this point here, if I've got a singly symmetric section with different size flanges on the top and bottom, I can get a yield moment for the top flange and a yield moment for the bottom flange. And in all our calculations that you'll see later, we just use the lower of these two values. You know, you can't reach the yield moment on, let's say, the compression flange if you've already blown past Fy on the tension flange. Make sense? All right. Now, is the yield moment the ultimate maximum capacity of a steel beam? The answer is no. Okay. Steel beams can, theoretically, steel beams can withstand moments far beyond the yield moment, and you'll see why here in a second. Okay. Now, this slide in your handout probably looks like a mess, and it is because this is the best slide I think I've ever created. Okay. And you'll see why here in a second. All right. So what we're going to do is we're going to take this steel beam and we're going to apply some moment, okay? Now, over here on the right, I have the stress profile, okay? So here's the beam. I apply some moment. I propose that initially it starts to look something like this. So as I apply that moment, the stress gets larger and larger and larger until, bam, it hits some magical stress Fy at the top and bottom, okay? Now, we're assuming it's doubly symmetric for this, okay? Now, that particular moment right there is what I call the yield moment. However much moment I needed to apply to generate that stress profile is the yield moment, where I reached Fy at the extreme fibers, okay? Now, my question to you is what would happen if we kept increasing the moment, okay? Here's my point. It's Fy right here, the very top. What about right here? This hasn't reached Fy, right? Neither is this, or this, or this. I've only yielded this part of the beam right here. I have not yielded any of this, right? The web hasn't yielded. The rest of that flange hasn't yielded. So if I kept increasing the moment, this would happen, okay? That yielding would penetrate through the section, and I would reach a point somewhere like here, where I've reached Fy everywhere, okay? Does that make sense? This is the maximum capacity of a steel beam, and this is where we have plastified the entire cross-section, okay? This is the plastic moment. This is called MP. Now, for those of you who had steel design, that should be at least somewhat familiar. You might not have seen the fancy animation, but this concept should be somewhat familiar, right? If not, no big deal. We'll do some examples, and I think you'll see, oh, okay, this is starting to make sense. All right. So I propose to you that for a steel beam, the maximum moment that a steel beam can withstand is called the plastic moment. It's where the entire cross-section has reached Fy. Now, we need a means of computing this value. It's actually pretty straightforward, okay? Now, I want to introduce to you two different definitions, okay? Everybody in this room should have an understanding of what a centroid is, right? Now, how do you calculate a centroid for a cross-section? It's sum of AY over sum of A, right? Make sense? Okay. I propose that that's called the, another term for that is the elastic neutral axis, okay? The elastic neutral axis, where the moment of inertia is based off of, where your sigma equals my over I, your elastic stress distributions, we base it off that axis. I'm now going to introduce a new term to you called the plastic neutral axis, okay? The plastic neutral axis is where all the forces in compression, all the plastic forces in compression, equal all the plastic forces in tension, okay? If you had reinforced concrete design, you probably remember doing something similar to this. You take a singly reinforced concrete beam, and you say, all right, what are my tensile forces? Well, it's the area of steel times Fy, right? What's my compressive forces? 0.85 Fc prime times A times B. And you say, all right, I must determine what that depth of that stress block is such that C equals T. That is essentially a plastic neutral axis. That's a similar approach. We're going to do something very similar here, okay? Now, I've got an elastic neutral axis and a plastic neutral axis. Are they the same thing? Not necessarily, okay? If you have a doubly symmetric shape, you know, like a W30 by 90, like a rolled W shape, well then, yeah, the elastic neutral axis and the plastic neutral axis are going to be in the same spot. But if you have a singly symmetric shape, kind of like all the bridge beams we've been looking at this semester, they're not going to be in the same place, okay? So if I have a doubly symmetric section, the elastic neutral axis and the plastic neutral axis are going to be in the same spot. As soon as that section becomes singly symmetric, that no longer becomes the case. And what ends up happening is that plastic neutral axis is going to shift in order to maintain the C equals T, okay? And you'll see that happen here in a second. All right, everybody good so far? Now, how do we determine the plastic moment? Well, once we find that location of C equals T, you know, where the compressive forces equal the tensile forces, it's pretty straightforward. How do you determine a moment? It's a force times a distance, right? Well, I propose to you that the plastic moment is going to be the compressive force times that moment arm plus the tensile force times that moment arm, right? And if everything's comprised of the same steel, how do I find that force? Well, it's just Fy times the area. So I say Fy times the area times the moment arm plus Fy times the area times the moment arm. Factor out the Fy, and that term in the parentheses, if you remember your steel design, is a very critical term when you studied beams, and it's called a plastic section modulus, or ZX. So Sx was a elastic section modulus, Zx a plastic section modulus. My steel design folks, you should remember that, right? Okay. No worries, we're going to have an example discussing that. Now, Zx is only a useful term if you are looking at a homogeneous section. In other words, everything being 50 KSI steel. As soon as you make one of those tension flanges 70 KSI or change the yield stress, then Zx becomes meaningless. Okay, and you actually don't see Zx in the bridge spec, but we're going to use it to at least get jog your memory on all this steel design stuff. Now, if you use different grades of steel for different elements in the beam, we call that a hybrid girder. And there are very significant advantages to using a hybrid girder, especially if you've got really long spans. Now, if you take your tension flange and use a higher grade of steel, there's a good chance you can probably trim some weight off of that flange and ultimately save some money. Okay? That's the positive aspects of using a hybrid girder. The negative aspect is that if you take a hybrid girder, Or if you take an I-beam and if you use, let's say, a higher grade steel on one of the flanges, you can take that flange and make it smaller, okay? That's great and everything. But what happens to your moment of inertia if you make a flange smaller? What happens to the moment of inertia? It goes down, right? Now, if the moment of inertia goes down, what happens to your deflections? They get larger, right? So sometimes, you know, you're perfectly fine on stress limits, but because of that damn L/800 limit in the spec, you're actually losing the benefit of that hybrid girder. I'm not saying never use them. I'm just saying be wary. All right. Sound good? All right. Just to get everybody's brains, you know, chugging and thinking a little bit about plastic moments and all this stuff, I've cooked up a pretty basic example. If you've had me for steel design, we actually did this same example in there, but we'll be able to do this pretty quickly. So we're going to assume that everything here has a yield stress of 50 KSI, and we're going to compute the plastic moment. Now, another thing we're going to do, we're going to look later on at the elastic stress distribution, because I want to show you that the centroid and the plastic neutral axis are not in the same spot. Okay, sound good? Now, in order to determine ZX, we have to find the point where all the compression equals all the tension, right? Now, since everything's the same grade of steel, I propose this is going to be pretty basic. We need to find the point where all the area up above equals all the area below, okay? Now, it's not the same thing as the centroid, and we'll see that here in a second. All right. Let me screen clip this because I'm lazy. Ooh, that is very big. Just want to shut up a little bit. Okay, all right. So we'll say MP example. Okay. All right. Now, here's my I-beam, and my goal is to try and find that magic point where all the area above the axis equals all the area below. So I propose that's going to be somewhere in the web. I don't know where, but somewhere in the web. Is that a reasonable guess? Okay. So I propose that it's going to be somewhere about, I don't know, right there. Okay? And I'm going to propose that this distance, we're going to call that x for now, okay? Now, if this distance is x, what does it make that distance? Was that what? 18 minus x. So far, so good? And I propose this is the location of the plastic neutral axis. All right. So far, so good? Now, if I load this thing normally, you know, put a load on the top of this beam, everything above this plastic neutral axis is going to be in compression. Sound good? So let's compute the area in compression. So the area in compression is everything that's shaded red. All this shaded area here and all this shaded area here. This is all the area in compression. Okay? So the area in compression, I propose, equals, bless you, 12 times 1.5 plus 1 point, or let me use my inches, plus 1.25 inches times x. Fair statement? All right, and what is, what's 12 times 1.5? That's what, 18? So, and since everything's in inches, I'm going to be a little loose with that. So 18 plus 1.25 x. Okay, now that's the area in compression. The area in tension is going to be this blue shaded area right here. All this and all that, right? Okay. So what's the area in tension? Well, I propose it's right? Plus 1.25 times what? 18 minus x, right? So what is that? What's 16 times 1.75? 28. So this is 28. Hold on. And again, I'm just going to leave the units off since everything's in inches. Plus, okay, what's 1.25 times 18? 22.5 minus 1.25x. Fair point? Okay, so what's 28 plus 22.5? What is that? What's that? 50.5 minus 1.25x. So far, so good? Any questions? Now, I propose that to find that location, we have to set AC equal to AT. So far, so good? So that is, what, 18 plus 1.25x has got to equal 50.5 minus 1.25x, right? Now, I'm going to get all the x's over onto one side by adding 1.25x, right? So that's going to cancel everything over here, right? And then I'm going to subtract 18 and get 32.5 is 2.5x. All right, I don't know why, but I'm getting the feeling there's an error here in some of the calcs, because this should come out to be x equals 5. So hold on. Okay, what was it? What? All right, hold on. What is 6? Hold on. Let's look over here at the area and tension. What is 16 times 1.75? 28. All right. Plus, what is 1.25 times 18? 22.5 minus x. So 1.25x. All right, so that is 50.5 minus. Oh, I know what it is. I know what it is. I think I do. All right, so this is 50.5. What does this come out to equal? 13. Okay, all right. That's what it is. 5 on the other end. Whoops. Sorry. That distance is 5. Sorry. I'm looking too far ahead. That's what it is. Okay. So I propose then that I'm going to redraw the beam. So that was all right. I just got a little paranoid there. I propose then that the plastic neutral axis is somewhere right here, where this distance is 5 inches. Sound good? Okay. All right. Now, in order to determine Zx, okay, Zx is basically just your area times your moment arm. In other words, it's the sum of A times Y. Okay? So you can do this however you want. If you want to break it up into a table, that's fine. It's pretty straightforward. Okay? Now, let's recognize a couple things. So this is, was that 18 times 1.25? Yep. This is 12 times 1.5. And this is 16 times 1.75, right? So if you want, you can say, all right, let's look at a shape Let's look at an area. Oh, got ahead of myself. Let's look at a moment arm. And let's look at AY. Okay, so we'll just keep this simple. Let's start off with shape 1, this top flange. Okay, so what's the area? What was that? 12 times 1.5, that's 18? Okay, all right. Now, moment arm. How far is it from the P&A to the center of this flange? Well, it's what? 13 plus what? Half that thickness? 13.75. Sound good? So 13.75. And then what is 18 times that? 247.5. Sound good? All right. Now shape 2, we'll say shape 2 is this one. And it's just that, just everything above, okay? So what's the area of that? Well, it's 1.25 times what? 13, so what is that? 16.25. All right, now what's the moment arm going to be? If this is 13 right here, there we go. If that's 13, then that makes this 6.5. And what does that come out to be? 105, and it's like what, 0.625? Okay, all right. Okay, now shape 3, we'll say shape 3 is all of that. So shape 3 is 5 times 1.25 or 6.25. And that moment arm is going to be what? 2.5? So far, so good? Okay, so what do we get? And the last one, we're going to look at this. So 4, you want? So 16 times 1.75 is 28. This time I'm going to trust y'all's calculations. I'm not going to say, oh, I think that's wrong, when I was messed up on that. Okay, now the centroid is, we're going 5, and then half of, what, 1.75? So what is that? 5.875. And add all that up, or multiply that, and what do you get? And add all that up, and what do you get? It's like 500 something. Do I have a second on that? 533. Is that what everybody else is getting? Okay, all right. And the units on that are cubic inches. Okay? So I propose that ZX is 533.25 cubic inches. Okay? Now that's ZX, so if I want to get MP, it's FY ZX, or 50 KSI times 533.25. And what does that give us? One more 6. 2.5. And then what are the units? Because if I have kips per square inch times inches cubed, that's inch kips. Now, moments, we tend to express moments in what? Foot kips? So how do I go from inch kips to foot kips? No. 12. Divide by 12. So what's that divided by 12? 2,000 what? Point. So we'll say 88. All right. It's been a while, but I know you all have done a calculation like that before. Am I correct? I know that you all did it because I taught you how to do it. And I know that if you've had steel design, you had to have done that before. All right. So far, so good? Getting you thinking about this stuff, right? It's been a while. Okay. Any questions? Okay. Now, one point I wanted to make is our plastic neutral axis was what? 5 from here? 5 from right there. So from the very, very bottom, what? 6.75? Is that right? 6.75 from the very, very bottom. Let's go back to this. Let's go back to... remember this? Let's go in and enter the data for this girder. I mean, the top flange is what? 1.5 by 12? Did I get that right? What is it? Yeah, 1.5 by 12. The web is what? 1.25 by 18. And then 1.75 by 16. Now, let's go down here. I mean, how do you calculate the centroid? You take, what, sum of AY divided by sum of A? So equals that divided by that. That is not 6.75, right? The plastic neutral axis from the bottom is 6.75. The centroid, the elastic neutral axis, is about 9.2 something, 9.27 something. Why are they different? Because you're calculating different things. Centroid is sum of AY over sum of A. The plastic neutral axis is where the area above equals the area below. It's not necessarily the same thing. So, all right. Sound good? Okay. I'm not saving changes. I don't know why I did that. Okay. All right. Any questions? Okay, now, let's go into composite beams. Let's see what's different. So everything I talked about just now was non-composite, just a steel beam by itself. Now let's look at composite beams, okay? Now, for steel beams, now what do I mean by composite? I mean steel and concrete. So composite beams, let's talk about steel first. How do you calculate the ultimate capacity of a steel beam? Well, the plastic moment capacity is Fy times Zx. How do you calculate Zx? It's just the sum of those AYs, right? We just did that. Now, that's steel. What about reinforced concrete? Well, you all have done this stuff before too, right? What's the tensile force? ASFY. What's the compressive force? What's 0.85 FC prime AB, right? Find that A distance to where C equals T, and then there's your nominal moment capacity, right? Everybody in this room has seen something like that before, am I correct? All right. So what we're going to try and do is kind of combine those two ideas to determine what is MP for a composite beam, okay? So what do I mean by combining those ideas? Well, we assume that all the steel reaches Fy, and for the concrete, we assume it reaches 0.85 FC prime, right? Then we just find that point where C equals T, and that's it. Now for the concrete, you all should remember concrete is a material that behaves very well in compression, not so hot in tension, right? So we're going to assume all the concrete in compression has 0.85 FC prime. In tension, no stress at all. And that's basically all there is to it, okay? Now, because of the geometry and because of the complexity with the different materials, there's a couple of different options, okay? And this is something I kind of glossed over on the last example, but this is really worth mentioning, okay? Let me go back to this example because I want to use this for discussion purposes. At the very beginning, I made a guess, and I just said, let's just guess that the plastic neutral axis is somewhere in that web, and I solved for X. Now, earlier, I guess I had a little weirded out mode because X came out to be 13 and I just don't have a good memory. But what if X had come out to be like 20? Would that have made would that have made any sense? No, the web is only 18 inches deep, okay? So if I had guessed that the neutral axis was in the web and I got an X equals 20 inches, it probably means I guessed wrong and the plastic neutral axis isn't in the web. Maybe it's actually in the top flange. Maybe it's actually in the bottom flange, okay? In composite beams, stuff like that is very, very common. There's a possibility that the plastic neutral axis is in the slab. There's a possibility that the plastic neutral axis is somewhere in the top flange. There's also a possibility it's in the web, okay? We don't know because we have to go through and test them all out, okay? Now, one of the things that sucks is that if you wanted to try and derive equations for all those different aspects, the algebra can get a little funky and a little long real quickly. Luckily, we don't have to do that, okay? If you all remember, I gave you a slide packet last time, but I also gave you a piece of the code, right? It should begin with something that looks like this. Let me load it up. Should look like this on the top. Everybody have this? Okay. If you remember, the code is broken up into 15 sections. Remember, section 3 had all our load stuff. Section 4 had those live load distribution factors. You all remember that? Okay. This is a piece out of section 6, the section on steel structures. Okay. Now, this appendix is particularly Appendix D. This is going to become very important for us for the next little bit. I mean, look at what the title of it is. Fundamental Calculations for Flexural Members. Okay. This appendix provides some very nifty guides for us to compute some of these things. The first thing it shows us how to do is to compute plastic moments. So let me go to the next page. This is a pretty straightforward plug and chug guide for calculating plastic moments. So if you look, I've got a number of cases. Case 1, the plastic neutral axis is in the web. Case 2, it's in the top flange. Case 3, et cetera, et cetera. Okay? For case 1 to be true, the plastic force in the tensile flange and in the web must be greater than or equal to the plastic force in the concrete or the compression flange, the plastic force in the slab, and the plastic forces in the reinforcement. All right, so far so good? If that were to be the case, this Y bar, that's P and A, that's the plastic neutral axis. I would calculate Y bar, plug and chug, calculate MP, plug and chug. If this condition is not met, go to case 2, plug and chug. If not, so on and so forth. Sound good? It's a really nice spreadsheetable plug and chug set of calculations. Okay? So, let's see. All right. Okay, that is a typo. I have here, you can see where I copy and pasted slides. That should be, positive bending region. Sorry about that. All right. So this is just that same screenshot you were looking at. This is out of the code. Now, we're going to take what you're looking at right now, those guides in the spec, and we're going to make them even easier. Okay? In positive bending, let me actually go back to this. Okay? So this is the first table for positive bending, and if you notice, it's a function of 6 terms. Okay? The plastic forces in each of the flanges, the plastic force in the slab, and then the plastic forces in the reinforcement. Okay? I propose to you that in positive bending, the reinforcement doesn't really do a whole lot for you. So much so that any of these terms with an RB and an RT, set them equal to 0. Okay? You do that, you will take those 7 cases and turn them into 3. Either in the web, in the top flange, or in the slab, in the deck. And if you don't believe me, take any one of these cases 3 through 7, set the reinforcement terms equal to 0, and you will see, you will literally get the same equation each time. Because those are all trying to determine Well, is it in the deck above this layer, below that layer, in between the two layers, and so on and so forth? Okay? So in positive bending, we really only need to consider 3 cases. In negative bending, we don't have the slab at all. We do have to consider the rebar, but we don't have the slab. Because of just the physics of it, there's really only 2 cases we have to consider in negative bending as well. So in the flange or in the web. So it's pretty easy. And again, very plug and chug. The only thing that takes a little bit of attention and a little bit of care are these little d distances. And we're going to have an example where we compute this later on. But these little d distances are from the plastic neutral axis to the individual components. So to the tension flange, to the compression flange, to the slab, et cetera, et cetera. Depending upon what case you're in, those distances can change. So you just got to make sure you're calculating them appropriately. Don't worry, we'll have an example on this. All right, and I'll show you just something real quick. So if you look at the bottom of that page, you'll see, here's case 1. So when you calculate y bar, you're calculating that plastic neutral axis, and they're saying it's going from the top flange down. If it's case 2, it's from the top of the top flange down, or case 3 from the top of the slab down. You just got to make sure you're computing your distances appropriately. Sound good? Okay. All right. Let me see something else. Okay. I have a couple other things I want to talk about, then we're going to take a break. I want to talk about the yield moment, okay? Now, if you remember for a non-composite beam, it was just this, right? It was Fy times Zx. That is not the case for a composite beam. This becomes a little more complicated because of the progression of loads. And the easiest way to explain that is to look at this, okay? So what I have here is a composite steel beam and a bridge. So here's the steel beam, here's the deck. Keep in mind, conduct that thought experiment. What happens? I take that beam, I set it on the supports, I put the formwork, the cross frames, the studs, the rebar, and I pour the deck. All of those moments, the first stage of dead load moments, go just on the steel beam, right? Then what happens? The concrete deck cures, and now I have a whole new moment of inertia, a whole new set of section properties, right? I then take that composite section and I put the future wearing surface. I put the barriers. I put the utilities. I put all of that stuff on there, right? Make sense? All right? So now I have a whole new set of moments applied to the long-term composite section. So those are all my dead load moments. What I have to do is figure out how much additional moment would be applied to the short-term section to cause yielding. And what do I mean? Well, if you take this stress profile, add it to this one, and add it to this one, you're going to get a stress profile that looks something like this. And why is there the jump? Because there weren't any stresses in the concrete deck over here, because there was no concrete deck. It didn't exist. That's when you were pouring wet concrete. It didn't become a composite slab until it cured, right? So it's not as simple as just finding the centroid and just saying, there you go. You have to consider that progression of stresses. Make sense? Now luckily, it's not terribly difficult. It is a nice plug and chug expression. So what do I mean by that? Well, I propose that we're adding up stresses, okay? The non-composite section is seeing some moments, so moment over section modulus gives you some stress. The long-term section is seeing some moments, so moment over section modulus gives you some stress. What we need to do is figure out how much additional moment goes on the section such that that moment over that section modulus, add them all up, hits Fy. So we set this equation up, solve for the additional moment, and then once we get that additional moment, we can say all the moments that were on there before plus whatever's necessary, that equals My. Make sense? It's not complicated. It's just, you got to think about it a little bit. That make sense? Everybody good? Okay. Excuse me. We're not going to spend a lot of time on this right now, but I thought I would mention it. One of the parameters that's going to become real important to us later and can be a little confusing depending upon what you're looking at is the depth of the web and compression. In other words, if I'm looking at some stress distribution, I'm saying right here the depth of the web that is seeing compressive stresses. It's not necessarily the centroid because you got to go with that progression of stresses. Make sense? Now, sometimes it is the centroid. I mean, if you're looking at, a deck casting sequence and it's just the girder and you're pouring wet concrete on there, well, there's no concrete deck on there at all. It is the centroid. This is the one thing I think takes a little bit of attention in here, and got to pay attention to what you're doing, okay? But the reason why it's so important is because later on when we look at buckling capacities and stability and what have you, you're going to see a lot of D sub C's, and it stands for how much of that web is in compression, all right? Sound good? Now, there is a depth of web in compression for the elastic range. Luckily, there's a really nice little plug and chug expression. You just take all your compressive stresses and your tensile stresses, plug and chug. It's pretty straightforward. For the plastic range, and I'm going to skip some of this. This is just some later stuff on service too, whether or not you can use the stresses or not. In the plastic range, you're looking at the depth of web in compression at MP. We actually are going to calculate this today, but there really isn't any calculation. I don't want to spoil it, but you'll see what I mean. But basically, at MP, how much of the web is in compression? And I'll leave it at that. What else? I think I already mentioned that. That I want to talk about later. That takes a little bit of discussion. Let's do this. I don't want to information overload you tonight. So this is what I think we're going to do. Let's take a little bit of a break. When we come back, we're going to take this example one, the same example that we've been looking at for the past few weeks, and we're going to compute MP and MY for this girder. Okay? Then we'll come back and look at the depth of web and compression in given areas. We're going to look at the hybrid girder factor and what have you, and come back to all that. I do not want to get into information overload. I would rather take my time. We're making very good progress in here. And the last thing I want to do is rush stuff because this can sort of fly at you really quickly and you need to approach it with a little bit of finesse. So let's take a little break and we'll come back later. Sound good? All right.